So our last speaker for this session is Ankit, and is going to tell us about a MPC in a communication local setting with adaptive security.
Okay. Hello, everyone. My name is Ankit, and this is a joint work with Nishant, Juan, Rafi, and Vasilis. So let's begin. So I'm sure most of you know of a bunch of commonly studied metrics of efficiency and scalability in multi-party computation, like communication complexity, computational complexity, round complexity, and so on. But a very common thing in most standard MPC protocols is that in these protocols, every party talks to every other party. And this can be a hurdle to scalability in situations where you have, let's say, millions of parties, and it's not possible for every pair of parties to have a point-to-point channel between them. So this is where this topic of communication locality comes in, which was first explicitly defined by Boyle, Goldwasser, and Tesaro in 2013 as the number of point-to-point channels that is used by each party. But it was already implicit in a bunch of previous works on something called almost everywhere secure protocols, which basically have multi-party computation over an incomplete network, but where we cannot guarantee the security of all of the parties, so some sublinear number of parties are doomed, so to speak. But we want security for all the parties, so we consider a slightly different model, as I will mention later. In standard MPC protocols, the communication locality is, of course, n-1, because every party talks to everyone else. And the question posed in BGT 13 was, can we have MPC with low communication locality, which is sublinear in the number of parties? I should specify here that this is different from the talk you just heard from Daniel, in which the connectivity was actually linear. We want to go for sublinear locality, so we assume a different model, which will become clear in a moment. And for this talk, I'm going to use sublinear synonymously with polylogarithmic, because it turns out that you need strictly greater than logarithmic connectivity for this kind of MPC. And this is just going to be called communication local MPC, or CLMPC for short. So coming to the model, we assume a complete graph where all n parties are connected to each other, and they dynamically select which channels to use. As a side note, we cannot have just a static incomplete graph, because an adaptive adversary could just, or any adversary could just pick a party that it doesn't like and surround it, like kill all of its neighbors, and then this party becomes isolated from everyone else. And we also assume synchronous communication, so protocols proceed in rounds. And this is everything we know about communication local MPC right now. So you can see the first result by BGT 13 considered static adversaries, and they showed that CLMPC is feasible for strictly less than 1/3 minus epsilon corruption. This was improved by the work of Chandran et al. In 2015, where they extended it to adaptive security, and they showed feasibility for an honest majority, but assuming an atomicity assumption on an operation called atomic multisend and erase, which is essentially this operation where a party can multi-send a message to a bunch of receivers and then erase the identities of these recipients from its internal state, all before the adaptive adversary can come and corrupt it. What we do in this work is we break down this atomic multi-send and erase assumption into separate assumptions, an erasure operation and an atomic multi-send operation, and we prove these 4 results. So focusing on this little part of the table, our first result is that in the absence of erasures, it is impossible to have CLMPC with, from a broad class of protocols called store and forward protocols, for any adversary corrupting a linear fraction, a linear number of parties. Second, assuming erasures, we show feasibility for honest majority from weak cryptographic assumptions. Third, assuming no atomic multisend, we show impossibility for a dishonest majority, again for store and forward protocols. And finally, without relying on any atomicity assumptions at all, we show feasibility for an honest majority, but from strong cryptographic assumptions. And in this talk, I'll be talking about the first impossibility and the last feasibility result. To begin, some background ideas from the work of Chandran et al. From 2015. The first thing that they introduced was something called a hidden graph, And the intuition here is that adaptive security is impossible if the adversary knows the communication graph. And like I mentioned, the idea is that an adversary could just corrupt all of the neighbors of some particular party. And this isolates the party from the rest of the network. And we go back to the notion of almost everywhere security, which we want to avoid. And the way to get around this is to have a hidden graph setup where every party only sees its own neighborhood. So the adversary sees only the neighborhoods of the corrupted parties. And particularly, the adversary is not notified when two honest parties are communicating. And how do we set this up? We just use a symmetric key infrastructure, and we let every pair of parties use their shared secret to non-interactively decide if they have an edge between them. Next, there is this idea of reliable message transmission, which seems to be a common theme in the talks this TCC. The sender and receiver are trying to communicate using a bunch of cables that are available to them, and there is this annoying adversary with a pair of scissors who is trying to cut the cables and isolate them from each other. In the hidden graph setting, it looks something like this, where there are a bunch of relayer nodes, and the adversary corrupts some subset of these nodes. And it turns into this so-called graph discovery game, where the adversary is trying to find a set of nodes that it can delete from this graph in order to disconnect the sender and the receiver. And it turns out that RMT is a fundamental building block of any MPC protocol in the communication local setting. So what we do is we prove our results for RMT and then extrapolate it to MPC. And today I'm only going to talk about RMT results because I don't have time for the MPC extensions. Coming to our first result, which is an impossibility in the absence of erasures for store and forward protocols. So first of all, what are store and forward protocols? These are just the most basic kind of structure that you can find in any message propagation protocol or gossip protocol, where the sender has a message M and it signs it with a signature sigma. The sender can send M sigma to any of its neighbors in any round. And a relayer node who receives M comma sigma checks the validity of the signature and then forwards it to a bunch of neighbors. And this basically covers all of the message propagation protocols in previous communication local literature and most gossip protocols in general. And we will show that such protocols cannot be used for reliable message transmission in the absence of erasures. And the proof sketch here is basically, we first show that there is some sender-receiver pair, which is separated by a distance that is greater than this some little L, which is order of log n over log n. And this is just a counting argument based on the polylogarithmic degree of the graph. And then the adversarial strategy is that when this message has traveled L hops away from the sender, so it hasn't reached the receiver yet, the adversary just goes and randomly corrupts a constant fraction of the parties. Specifically, I think it's 1/4 of its corruption threshold. And then using another property of all known store and forward protocols, we actually show that at least one party gets corrupted in the communication subgraph of each neighbor of the sender. And finally, this is sufficient for the adversary to block the transmission, as I will now show. So let's say there is this sender who has propagated its message into all of these nodes in the network, and then the adversary hits this one node in the middle. What the adversary can do, since there are no erasures, the adversary can check where this message came from, go back and corrupt that neighbor, once again check where it came from, go back and corrupt him. And now it has reached a neighbor of the sender, so what it can do now is check the outgoing edges where the message was forwarded. So it goes ahead and corrupts these two, then these four, and finally everyone is killed. And we know the receiver was not in this because this has only a length of L. And so all of the parties except the sender who have the message have been corrupted, and the transmission is blocked. And we show that this can be done without exceeding the corruption budget of the adversary. And this concludes our impossibility result for store and forward RMT. This can be extended to MPC quite easily because RMT is a special case of MPC after all. And we next come to our final feasibility result, which does not rely on any atomicity assumptions, and it shows communication local MPC for honest majority from strong assumptions. And the assumptions we use here are a public key infrastructure, a hidden graph setup, trapdoor permutations with a reverse domain sampler, and compact and malicious circuit private fully homomorphic encryption. So very strong assumptions. And we show that there is a polylogarithmic round communication local protocol for RMT for a single pair of parties, tolerating adaptive corruption of some constant fraction of the parties. The polylogarithmic rounds comes from the fact that the hidden graph, the way I showed the sampling of the hidden graph, it is an expander with high probability, with polylogarithmic expansion and hence polylogarithmic diameter. And the main insight here is that we hide the store and forward protocol under the hood of fully homomorphic encryption. So earlier, where we had each node checking the signature and then picking a valid pair and forwarding it, we now do it all under FHE. So the relayer gets a ciphertext with the message, and it runs the evaluation algorithm on the verification and selection circuit. And this is the ciphertext that is then forwarded. Now, it's not, and why is this helpful? Because then we can have the honest parties just spam decoy messages in the network, and then a corrupted node just sees a bunch of ciphertexts coming from all directions, and it doesn't know which one has the real message. So even though there are no erasures, the adversary can't do anything in this setting. Now it is not so simple, and there are several caveats that we need to deal with. Firstly, the ciphertext size may reveal the position of the relayer in the hidden graph. So what we do is we adjust the size of the decoy messages according to the size of the ciphertext as it grows. And we cannot have the ciphertext grow too much, so we need compact, fully homomorphic encryption for efficiency reasons. Secondly, the adversary can feed malicious ciphertexts into the network, and FAG evaluation is technically only defined for honestly generated ciphertext. So to avoid leaking information through the evaluation procedure, we need FHE to be maliciously circuit private. Third, there is this impossibility result from Katz et al. In 2013, which says that we cannot have FHE with both compactness and adaptive security at the same time. And we get around this by just making a scheme for our specific function. And we only need FHE to evaluate this one function, which verifies signatures and picks the first pair with valid signature. And this scheme is just a simple embedding of non-committing encryption inside a plain FHE scheme. And now we have a single pair RMT protocol, so RMT from one sender to one receiver, and the next job is to extend this to RMT between all pairs of parties, because we need everyone to talk to everyone over this low-degree network if we want MPC. And the natural idea is to do parallel composition, which actually happens to work for our other feasibility result in the presence of erasures. But without erasures, this does not work, as you can see from this example, where you have a sender with message 1 for a corrupted receiver and message 2 for an honest receiver. The corrupted receiver is closer in the graph. So when the sender propagates these messages, it hits the corrupted receiver first. And now the receiver can just do what we saw earlier, the same attack. Because it can identify the message intended for itself, and these messages are bundled together. So it just goes back and corrupts this guy, corrupts the neighbor, and then just kills everyone who has the message. And receiver 2 does not get the message intended for it. Now, we cannot avoid this kind of bundling of messages in this setting because we have n number of messages going from the sender and only polylogarithmic locality. So the best we can just do is all to polylogarithmic RMT instead of all to all RMT. So now we have n senders and only polylog n parties acting as receivers. The way to do this is to just use an independent hidden graph for each of the receivers. And the adversary can only interfere with the hidden graphs of corrupt receivers. The hidden graphs of the honest receivers are safe. And this we call sublinear output set RMT, since a sublinear number of parties get the output. And this is abbreviated to SOS RMT. And this can be used to achieve SOS MPC, where MPC output is delivered to a sublinear number of parties. And we have these open problems. So all to all RMT is open. RMT from weaker assumptions, since we showed it from strong assumptions, and RMT in the asynchronous model, which is a work in progress. And that's all. Thank you for listening. You can find our paper on ePrint.
So we have time for questions.
Thank you for the very nice talk. I have a question about one of your open problems here. So all-to-all RMT, how is that related to parallel broadcast? Because so we have some result which you might be aware of, like a parallel broadcast, and we use kind of similar techniques of basically hiding the communication graph. So I'm wondering how that relates to all-to-all RMT.
I see. So, as I said, our protocol cannot be composed in parallel when we have one sender to multiple receivers. So a broadcast kind of thing cannot be done with this. We can have multiple senders to one receiver, but yeah, broadcast is not something we can achieve with our techniques. So maybe.
So, but all-to-all RMT would mean everybody
Yes.
sends to everybody.
Yes.
Yeah. Okay.
But we do not
Maybe we
achieve
can
that.
talk for a moment offline.
Yeah, of
That's okay. Good. Thanks.
More questions? So let's thank Ankit and all the speakers of this session.